For centuries, mathematics was a perfect crystal palace built on the bedrock of logic. Every statement was either true or false, and it was believed that every true statement could eventually be proven. An unsolvable problem was just a challenge waiting for a brilliant mind. But in the early 20th century, this entire edifice was shaken to its core. A single, unsolvable problem emerged from the heart of pure logic, revealing that the palace of mathematics contained truths that could never be proven. It was a discovery that redefined not just math, but our understanding of truth, knowledge, and computation itself. This is the story of how the quest for absolute certainty led to the discovery of its impossibility. At the turn of the 20th century, math was facing a deep foundational crisis. New ideas, like Georg Cantor's theory of different sizes of infinity, had led to strange and troubling paradoxes. The most famous was Russell's paradox. Imagine a set that contains all sets that do not contain themselves. Now ask yourself, does this set contain itself? If it does, then by its own definition, it should NT. But if it doesn't, then it should. This simple question created a logical contradiction that threatened to unravel the very fabric of mathematics. Into this chaos stepped David Hilbert, one of the most influential mathematicians of his time. He saw the crisis not as a disaster, but as a challenge. He envisioned a grand program to place all of mathematics on a secure, unshakable footing, once and for all. This became known as Hilbert's program, and it had three audacious goals. First, completeness. Every mathematical statement could be proven either true or false. There would be no unknowable truths. Second, consistency. The system would be free from contradictions. You could never prove that a number is both prime and not prime at the same time. And third, decidability. There must exist a definite mechanical procedure, an algorithm that could determine the truth or falsity of any mathematical statement. Hilbert dreamed of a truth machine. A mathematician could feed any conjecture into this formal system, turn a crank, and out would pop a definitive proof. It was a utopian dream of absolute certainty. The brightest minds in logic set to work, completely unaware that a quiet logician from Vienna was about to demonstrate their quest was an impossible one. That quiet revolutionary was Kurt Gödel. In 1931, at just 25 years old, Gödel published a paper whose technical title, On Formally Undecidable Propositions, concealed a philosophical bombshell. In just a few dozen pages, he systematically dismantled Hilbert's dream with two devastating incompleteness theorems. The first incompleteness theorem states that in any consistent formal system, powerful enough to do basic arithmetic, there will always be statements that are true but can never be proven within that system. Gödel's genius was to devise a method that allowed mathematics to talk about itself. He invented what we call Gödel numbering, assigning a unique number to every symbol, formula, and proof in a formal system. This meant that a statement about the system, like "this formula is provable," could be translated into a mathematical equation about numbers. Logic became a part of arithmetic. Using this trick, Gödel constructed a mathematical statement that effectively said, "This statement is not provable. Let's call this statement G." Think about the implications. If you could prove statement G, the system would be proving the statement, "This statement is not provable." The system would be proving a falsehood, which makes the system inconsistent, a fatal flaw. But if you cannot prove statement G, then what it asserts, "This statement is not provable," is actually true. This means your system contains a true statement G that it cannot prove. The system is therefore incomplete, so any useful mathematical system must be incomplete. There will always be true statements that lie beyond the reach of proof. If that was a shock, Gödel's second incompleteness theorem was the final nail in the coffin for Hilbert's program. It's a direct consequence of the first theorem, and it states that no consistent formal system can prove its own consistency. The very statement "this system is consistent" can be translated into a mathematical formula. Gödel showed that if a system could prove this formula, it would lead to a contradiction, meaning the system was actually inconsistent. To prove a system is consistent, you always have to step outside of it, using more powerful, unproven assumptions. Certainty could never be found from within. The dream was over. Gödel had found a fundamental, inherent limitation of all formal logic. The pristine palace of math was, and always would be, unfinished. As Gödel was revealing the limits of proof, a young British mathematician named Alan Turing was attacking Hilbert's third goal, the decision problem, from a completely different angle. He wanted to know if there could be a single algorithm to determine if any given mathematical statement was provable. To answer this, Turing first had to define what an algorithm even was. In his 1936 paper, he introduced a brilliantly simple, abstract model of a computer. It wasn't a physical device, but a theoretical one, an infinitely long tape, a head that could read and write symbols, and a simple set of rules. This Turing machine became the foundational model for all of computer science. With this concept, Turing tackled a seemingly simple question that became known as the halting problem. The problem is this: can you write a single computer program that can take any other program and its input and determine, without actually running it, whether that program will eventually halt or run forever in an infinite loop? At first, this seems plausible, but Turing was asking for a universal decider, a single program to analyze any other program. His proof that such a program is impossible is a masterpiece of self-referential logic, much like Gödel's. Let's walk through it. Imagine a program to solve the halting problem actually exists. Well, call it halts. You give it a program and an input, and it returns true if the program halts, and false if it loops forever. Now, using halts, let's build a new mischievous program. We'll call it Paradox. Paradox takes the code of another program as its input. Then, it runs our hypothetical halts function on that program, feeding the program its own code as its input. And here's the twist. If halts says the program will halt, Paradox deliberately enters an infinite loop. If halts says the program will loop forever, Paradox immediately halts. Paradox does the exact opposite of whatever program it's analyzing. Now for the killer question. What happens when we feed the Paradox program its own source code? Let's run Paradox on Paradox. If our halts function determines that Paradox will halt, Paradox's own rules say it must loop forever. That's a contradiction. If halts determines that Paradox will loop forever, its rules say it must halt. Another contradiction. We're trapped. The only way out is to conclude our initial assumption was wrong. The universal program halts cannot possibly exist. The halting problem is undecidable. Turing had not only proven there's no universal algorithm for deciding mathematical truth, but he had also discovered a fundamental limit to computation. There are concrete problems that no computer, no matter how powerful, can ever solve. The connection between Gödel and Turing is profound. They are two sides of the same coin. Gödel's incompleteness is about the limits of logical proof. Turing's undecidability is about the limits of algorithmic computation. Gödel showed some truths are unprovable. Turing showed some problems are unsolvable. The twin revelations of Gödel and Turing sent a philosophical tsunami through science and philosophy. The old dream of absolute certainty was shattered, creating a new landscape of thought defined by fundamental limits, but also by a newfound appreciation for human creativity. The key distinction that emerged was between truth and provability. Gödel showed they are not the same thing. There is a realm of mathematical truths that exists outside the confines of any formal system. Truths we might grasp with intuition, but can never formally prove. This had a surprisingly humanizing effect. If theorems couldn't just be churned out by a machine, then the creativity and ingenuity of the human mathematician were paramount. Mathematics became an endlessly creative endeavor, not a finite set of facts to be cataloged. At the same time, this work laid the groundwork for the digital age. Turing's abstract machine, conceived to explore logic's limits, accidentally became the blueprint for the modern computer. The universal Turing machine, one that could simulate any other by reading instructions from its tape, is the theoretical forerunner of today's computers that load software to perform any task. And the halting problem became a cornerstone of computer science. It has real-world consequences. For example, it's impossible to create a perfect antivirus program that can detect all possible viruses, because that would be equivalent to solving the halting problem. It's impossible to write a program that can definitively prove any other piece of software is bug-free. The shock waves also revealed a new kind of unsolvability. The most famous example is the continuum hypothesis. In the 1870s, Georg Cantor showed that infinities come in different sizes. The infinity of counting numbers 1, 2, 3 is smaller than the infinity of all numbers on the number line, including irrationals like pi. The continuum hypothesis asks, is there an infinite set whose size is strictly between those two infinities? For decades, no one could prove or disprove it. The final answer was stunning. In 1940, Kurt Gödel showed the continuum hypothesis cannot be disproven from the standard axioms of math. Then, in 1963, Paul Cohen showed it cannot be proven either. This meant the continuum hypothesis is independent of our standard mathematical framework. It is neither true nor false within that system. You are free to add it as a new rule, or add its negation as a rule, creating two different but equally consistent mathematical universes. It wasn't just that some truths were unprovable. Some statements had no inherent truth value at all. So, did this mean mathematics had failed? Far from it. The vast majority of mathematical work never touches these limits. But living in a world aware of them has profoundly shaped modern thought. The unsolvable is not a barrier, it's a new horizon. Gödel and Turing taught us that no single system, no single set of axioms can ever capture the entirety of truth. This has echoes everywhere. The search for a theory of everything in physics must contend with the possibility that any such theory might be fundamentally incomplete. In AI, it places a limit on what a purely logic-based intelligence can ever know, highlighting the importance of other forms of reasoning. The legacy of these unsolvable problems is a lesson in intellectual humility. They replaced a clockwork, deterministic universe with one that is more complex, more mysterious, and ultimately, more interesting. They showed that the pursuit of knowledge is not a finite task of filling in a map, but an infinite journey into a territory whose boundaries are always expanding. The formal systems we build are just tools, powerful but limited. The universe of truth itself is infinitely richer. The dream of absolute certainty was beautiful, but the reality of endless discovery is far more profound. Mathematics was not broken. It was liberated.